So today we'll be going over homogeneous higher order differential equations with constant coefficients. So first off, what exactly is a homogeneous or non-homogeneous differential equation? Let's say we have this differential equation 2x squared y double prime plus 3xy prime take away y is equal to 0. Now this is what we refer to it as being a homogeneous differential equation because it's equal to 0. Now, if we have a differential equation that's not equal to 0, for instance, some function g of x, then this, in fact, would be considered a non-homogeneous differential equation. And that's the only distinct difference between homogeneous and non-homogeneous differential equation. For homogeneous, the differential equation is equal to 0. For non-homogeneous, it is equal to some function. Let's call it g of x. So up to this point, we've learned several methods to solving first order linear differential equations, as well as a reduction of order to make a second order differential equation into a first order and solve accordingly. Now, what if we have higher order differential equations, second or third order perhaps? And in this particular case, we're going to be solving these higher order with constant coefficients. So we'll be looking at solutions in this form: y is equal to e to the power of r x. And so let's go ahead and do an example here. So for this example, we have the third derivative of y with respect to x. Take away dy dx is equal to 0. So first off, this is a homogeneous differential equation because it's equal to 0. It's a higher order, third order in this case, and it has constant coefficients, right? In this case, the coefficients will be 1. So in this case, this is what's called as a auxiliary equation or a characteristic equation, where we just replace the derivatives with this variable named r. So r cubed take away r is equal to 0. So this is the first step. Wherever you see a differential, that's where you replace with the variable r, and whatever order it is, that would be the exponent of the r. So r cubed take away r is equal to 0. And from here, you just find the roots of the equation. So we factor out r times r squared take away 1, and we see that r is equal to 0, positive 1, and negative 1. So we have the r values here. And since I mentioned previously, we're looking at the solution of this form: y is equal to e to the r x. So where whatever r's you get, you just plug it in. So the general solution for this particular example would be y of x is equal to c1 times e to the power of 0 times x. So any power to 0 is equal to 1. So you just have c1 plus arbitrary constant c2 times e to the x. In this case, it will be r is equal to 1 plus arbitrary constant 3 times e to the negative x. So r equals negative 1. So this is nothing more than the linear combinations of those roots that we found in the form e to the power of r x. And this is how you solve the homogeneous higher order differential equations with constant coefficients. Now, there are three general cases that you could actually come across using this method to solve, and we'll be going over each of the cases. So for case one here, would be having distinct roots. As the previous example, you have r being equal to specific constants. So let's go ahead and do another example just to reiterate. So you have 2 times the second derivative of y with respect to x, take away 5 dy dx, take away 3y is equal to 0. Now, of course, you see it's a homogeneous higher order, second order in this case, and we have constant coefficients 2, 5, and 3. So we could go ahead and use this method. So we have 2 times r squared take away 5r take away 3 is equal to 0. Now, just to reiterate, whenever you see a derivative, that's where you replace it with the variable r, and whatever order it is, that would be the exponent of that. So you have r here for being the first derivative, r to the power 1, and in this case, for the last one, take away 3. Since there is no derivative, you would just leave the constant on its own without using the variable r. And so for here, you just solve the roots of this equation. So you just factor the equation 2r plus 1 times r take away 3 and solve for the r's. So r1 is equal to 3 and r2 is equal to negative 1 half. Now from here, we're able to get the general solution of the differential equation easily. So you have y of x is equal to arbitrary constant c1 times e to the 3x plus your c2 e to the power of negative 1 half x. So for the first case, r is equal to different solutions, right? They're not equal to each other and so forth. They're not repeated. So this would be the first case of distinct roots. Now for case 2, you have multiple roots where you have the same r. So r1 is equal to 1 as well as r2 is equal to 1. So let's go ahead and do an example. So again, homogeneous higher order constant coefficients, where we could go ahead and use this method, which is the auxiliary equation, or the characteristic equation would be r squared take away 10r plus 25 is equal to 0, and just solve for the roots. So you see that r take away 5 squared is equal to 0, and you have r1 is equal to r2, so they're both equal to 5. So in this case, this is what you do here. The general solution would be equal to your c1 times e to the power of 5x, so this one stays the same, plus, but when it comes to the second root, this is where you would add a x, so you multiply the arbitrary constant times a x times e to the 5x. So this is a step for multiple roots. Whenever you repeat the same root, you multiply by an x in front of the e here. So this is your general solution to that differential equation. Now for case 3 is when you would have complex roots, such as having r1 is equal to alpha plus I beta and r2 is equal to alpha minus I beta. So in this case, this is what we're referring to the variables. The first variable is going to be referred to alpha, the second is beta. So in this case, we will be utilizing Euler's formula to be able to represent it in a different way. So for Euler's formula, we have the e to the power of the I theta is equal to cosine theta plus I sine theta. So you're able to represent it using sine and cosine. This is what we'll be utilizing when we solve for these roots. So let's go ahead and show an example. So we have y double prime plus 4y prime plus 7y is equal to 0. So we see it's homogeneous constant coefficients. Let's go ahead and get the auxiliary equation. So we have r squared plus 4r plus 7. So in this case, let's utilize the quadratic formula to solve for the roots. So we have r is equal to negative 4 plus or minus square root 16 to equate 28 divided by 2. Simplify a bit, and this is where you see the imaginary number coming in. So we have our r is equal to negative 2 plus or minus I times the square root of 3. So we see this one is referred to as alpha. This one is referred to as beta. Now remember Euler's formula, that's where we're going to be using sine and cosines for the general solution of this differential equation. So our solutions to these kinds of complex roots is e to the power of alpha x times cosine beta x plus, and as well as e to the alpha x sine beta x. So let's go ahead and get the general solution with this. So we have the general solution being y of x is equal to c1 e to the negative 2x times their cosine square root 3x plus c2 e to the negative 2x times sine square root 3 times x. So this is your general solution to the differential equation. So we've gone over the 3 different cases when you have distinct roots, when you have multiple roots of the same value, as well as having complex roots. This is how you utilize this method to easily solve for the general solution of the differential equation. It simplifies a bit using that characteristic equation, that variable r, and solving for the roots. So just to emphasize, this method is to use on higher order differential equations that are homogeneous, in other words, equal to 0, as well as them having constant coefficients. Now, for the next video, I'll be showing you how to solve non-homogeneous differential equations.